and welcome to Week 6, Lecture 2 of CO 442-642 Graph Theory. Today we'll be discussing well-quasi-ordering. So what is well-quasi-ordering? Well, let me remind you what a quasi-ordering is. A quasi-ordering is a relation that is both reflexive, so where every element is related to itself, that x is at most x, and transitive, that is, if x is at most y and y is at most z, implies that x is at most z. So this is a quasi-ordering. What is a well-quasi-ordering? Well, it's with an additional property about infinite sequences. Namely, here's the definition, a well-quasi-ordering is a quasi-ordering such that for every infinite sequence, x0, x1, off to infinity, there exists I less than j such that xi is at most xj. So there's always somehow, in any infinite sequence, there's always these at least two elements that are kind of related. So we call xi, xj a good pair. And then we say an infinite sequence is good if it has a good pair and bad otherwise. And in that language, a well-quasi-ordering just means that every infinite sequence is good. Okay, so that's all very formal and logic-based, but what's maybe some other thoughts on well-quasi-ordering? Well, maybe a different way to think about a well-quasi-ordering is you have a quasi-ordering is a well-quasi-ordering if and only if the set X then contains neither an infinite antichain nor a strictly decreasing sequence x0, x1, etc. So not having a strictly decreasing sequence is kind of natural, say if you're something more like the integers or have a value like for graphs, as you'll see, because maybe then you can't get infinitely decreasing, strictly decreasing. But an infinite antichain is maybe then more the point that you're forbidding. So there aren't kind of infinitely many incomparable odds. So if you exclude, we won't do this proof because the proof from D still uses Ramsey's theorem, which we haven't done yet. But it's not too hard. And then if you go through that proof as a corollary, you find something stronger is true. That if X is actually well quasi-ordered, then every infinite sequence in X has an infinite increasing subsequence. So you get this nice kind of not only a good pair, but a whole infinite, good pairs, an infinite increasing subsequence. So we'll need those basics. We won't prove those, but we'll use them. And now we can talk about for graphs. And what's the point? Well, we're doing minors, right? We're doing minors these weeks. The minor relation is obviously a quasi-ordering of graphs. It's reflexive, you're a minor of yourself, and it's transitive if x is a minor of y, y is a minor of z, then x is a minor of z. So that's the minor relation. The question is it a well-quasi-ordering? And this was a kind of a conjecture of Wagner from the 60s that the minor relation is a well-quasi-ordering. So what is that saying? Well, that, any infinite sequence of minors, you can find one that's a minor of another, which is a very bold statement to make. And by the facts we just discussed, it's equivalent to saying that there is not both an infinite antichain of minors. So you can't find an infinite family of graphs, no one a minor of another, and also no strictly decreasing. But of course for graphs you can't have a strictly, this is what I was suggesting, for finite graphs you can't have a strictly decreasing infinite sequence, right? Because a graph, if you have a minor, it has to be smaller, and then if it's decreased, proper minor smaller, there's graphs only have a finite number of vertices, it can only have finite such decreasing sequences. So really what the Wagner's conjecture is saying that there isn't an infinite antichain of graphs under the minor relation, that there isn't an infinite set of graphs which are pairwise, not minors of each other. So this was a very, thought of problem coming kind of, again, the motivation from Kuratowski's theorem from this Kuratowski sets. And it was indeed proved, and it's called the graph minor theorem by Robertson and Seymour. So basically they had this project in the 1980s that developed all this machinery, and what we'll be talking about for the next couple of weeks, tons of beautiful theorems and terminology to prove this theorem and other theorems like it. And now that has stretched to 2004, so even if they did the work in the 80s, they kept on going, the writing and the publishing. So now their graph minor series stretches 24 papers. It's been published until 2012. The proof for just this theorem arguably is found in 17 of these papers. So really the whole work, over 20 papers, it's hundreds of pages long to just prove this theorem, but many other good theorems come along the way. But because it's such a strong, this may be the most beautiful theorem in graph theory, the graph minor theorem, that this relation is a well-quasi-ordering. Why? Because, as a corollary, you get the Kuratowski set for any minor closed property is finite, right? And how would you really prove that otherwise? It's such a, looked at all the minor closed classes we looked at, surfaces, we didn't even know the list, but, this is saying they're finite. Now that theorem you could prove separately. It takes, maybe 50 or 30 pages, but would take work. But here it's not just for that, for any property, finite. Which is very crazy to say, but their theorem does it. So it's amazing in its generality, and of course we won't have time to do the proof or anything, but we'll explore some of the main ideas behind it. So today we'll be kind of looking at that, and we'll talk about it for trees, but I thought maybe just mention one application. So to see the power of this theorem. So another point is in their work, Robertson and Seymour actually established that there exists a cubic time algorithm to test if a graph contains a fixed graph H as a minor. So you tell me a graph, K4, K10, K33, whichever, some very large graph, there will be, think of that as fixed, so its number is a constant, then there is a cubic time algorithm. So cubic in the graph that you're testing, algorithm to test if it contains this fixed graph H as a minor, which seems not at all obvious, so we won't talk about that, but maybe we'll come back around to it when we talk about their theory some more. But okay, let's take that. So there is this nice polytime algorithm to test for a fixed graph as a minor. Why is that interesting? Well, here's a crazy application of the graph minor theorem. So we say a graph G is knotless if it can be embedded in R3 such that no cycle is knotted. So what do I mean? So if you remember linked lists from last lecture, where we embedded graphs in 3 space, and we said all graphs can be embedded in 3 space, but maybe not with additional properties. So we talked about linked. Well, here I won't draw a picture, or just wave my hands, but if you know about knots, that cycles can have curves in space could be knotted or not, the unknot, not less. So here it's saying that no cycle would be, that every cycle would be the unknot, that no cycle would be intrinsically knotted. And now, it might not be obvious to you, but it turns out not every graph can be done like this. For example, K7, they know, has no such knotless embedding. And once again, if you think about it, this is a minor closed property, right? Because deleting stuff won't create a knot, and again, contracting things, if you have a cycle that, you can't get a cycle that was knotted if it wasn't knotted before. Okay, that's all good and dandy, but why is this an application? What do I mean? Well, here's a startling fact. Before the graph minor theorem, it was open whether knotlessness, so deciding whether a given graph, generally given graph G, if it's knotless, if that question is even decidable. What do I mean by decidable? Whether any algorithm exists to decide if a graph is knotless. Is there any algorithm you can give me, I don't care about polytime, exponential, anything, to decide knotlessness? Is there any way to look at a graph and tell that it's knotless? And so this was open. However, now by the graph minor theorem, because knotlessness is a minor closed property, there must exist a finite Kuratowski set for it. We don't have any idea what the set is. I mean, we have some 20 plus graphs maybe that are minor minimal knotless that we know of, but could be many more. But we know it's finite. And so therefore, on a theoretical way, since we know it's finite, and we know Robertson-Seymour's theorem above that you can test a fixed graph as a minor, this implies that there exists a cubic time algorithm to decide if a graph is knotless. So this is a crazy result, right? Before this theorem, even whether there's an algorithm was open. Now there's a fast one, polytime, cubic time. We have no clue what the algorithm is, but we know it exists because we know the Kuratowski set is finite. So that's just one application to show that, really there are many nice minor closed properties out there, and this really tells you that testing, whether you're in one of those is actually nice and can be done in polytime. So that was an application. Maybe let's move on to we're going to try to prove the graph-minor theorem for trees. And in order to do that, let's talk about well-quasi-ordering for subsets. So here's a nice proposition that we're going to need, which is that if X is well-quasi-ordered, then so is the finite subsets of X, or finite sets coming from X. So why is this? So if you take finite sets of X, members of X, why are they well-quasi-ordered? So right, do you get the difference, right? So we know that in any infinite sequence of X, there's a good pair, but now we have kind of sets from X, and we want to show that they have a good pair. Well, how would you even prove this? So maybe, you could pause and think a moment. This is very hard. How would you prove this? Certainly there must be some kind of inductive thing, but now we're in the world of infinite. So if you're not used to these infinite things, it's hard to get out your head around how to do these kinds of proofs. But I'll start you out. So here's kind of the nice, clever way to do it. So this is kind of called the minimal bad sequence argument. So we'll see it again in a bit, but here it goes. So suppose not, so obviously we're doing contradiction. So what does it mean? If X is not well-quasi-ordered, there's a bad sequence. So what I'm going to do is I'm going to kind of say, okay, among all bad sequences, choose the first, they always have a start, some A0, choose the A0 that is minimized, whose set is minimized, right? So by set, I mean as that number of elements, right? So if we had a bad sequence where every set in it was just of size 1, that would be a contradiction. So choose A0 with minimum size. Then what do we do? Well, this extends, we can also, by that nature, it would extend to a bad sequence. Now, among all of those bad sequences, you choose the A1 of minimum size, and then we know that that extends to a bad sequence. And then among all those, you choose the A2 that has minimum size. So it's kind of like choose this thing subject to that. And now if you understand kind of infinite and compactness, it means you will end up getting, because we'll do this arbitrarily often, we'll get kind of an infinite sequence of these ANs, which with these nice properties, that each one was chosen kind of minimal among the rest. Okay, so that's what we'll do. So we have this kind of minimal bad sequence, and so it's not hard to then argue that the actual infinite sequence must in fact be a bad sequence, because if we had a good pair, it would show up somewhere finitely, and then we wouldn't have chosen that. So that's our starting base. So we have a minimal bad sequence. Now what do we do? Well, now that we have something to grasp with, well, for every n, you pick an an in an, so little an and big an, and you remove it and call those bn's. So what's the point? We're going to kind of use the minimality to try to, in a sense, inductively get down to the base case of just having one element in each set. All right, so now let's think through this. So what do we know? We've picked out one element from each set. Now what do we know? Well, since X is well-quasi-ordered, by our corollary earlier, not only do you get good pairs, you get infinite increasing subsequences. So again, we didn't prove that, but we'll just use it. So these ANs, these elements we pick out of our bad sequence, there must be not only a good pair among them, but an infinite increasing subsequence. So we'll call that ANI. So the NIs will be an N0 and N1, kind of increasing. So we don't know where they are, but let's just name their indices as such. Then what do we do with this? Well, by minimality of AN0, so let's think of the point where you have this N0. Then the sequence, if we looked at this, A0 up to AN0 minus 1, and then we're going to put in the B's. So here's where we're going to use the B's. So we have this starting infinite sequence. So I'll keep the original members to kind of say, okay, those were our decisions before. But from that point, I'll switch it up. So when we were going to put AN0, I'll put in BN0, right? I'll remove this AN0 from it. But then I won't keep continuing. Instead, let me go ahead and put in BN1, BN2, etc. So kind of at that point, I truncate, but I only pick up the truncated bits from my increasing good subsequence for the little ANs. And by minimality, do you agree that this sequence is good? Why? So maybe stop and think for a second. because again, it's the choice of the minimality of an0. Whenever we pick that, right, bn0 is smaller, so if it extended to a bad sequence, we would have picked bn0 instead. So it must be good. That's the power of this minimal bad sequence argument. And what does that mean? Well, think through. So it's good, so it has a good pair somewhere. So can it have a good pair in the first bit? You know, AI, AJ? No, because the ANs were a bad sequence. Could it have it between an A and a B? The answer is no, because if AI was less than or equal to BJ, well, BJ is a subset of AJ. So again, you'd find that that's true. So again, you get a good pair in the A's, which aren't allowed. So what does that mean? It means that the good pair that exists in this sequence must be of the form BI-BJ. So it must live in this truncated aftermath. But then if you go to that, so what does it mean? That means that BI kind of injectively as a subset goes into BJ, right? So for BI, there's an injective mapping where each element of BI is lower than some element of BJ, kind of in a matching inductive way. The BJ could be larger, but that's what we'd have. Well, since we know that AI is less than or equal to AJ, because it was an infinite increasing subsequence, then we can just add these, get back AI and AJ, and now we get this injective mapping keeping less than or equal, and this establishes that AI AJ is in fact a good pair, a contradiction. So think through, maybe go back through that argument if you haven't seen this before, but well-quasi-ordering, we picked a minimal bad sequence, and then we kind of said, oh, remove them, get an infinite increasing subsequence for the removed elements, and then we can use minimality and actually kind of induct it. You see how kind of the B's are kind of doing the inductive bit in a sense by the minimality, and then we add back our A's and get that we get a good pair. So that's for subsets. Now I want to do it for trees. So here's this theorem from Kraskol, 1960, that trees are well quasi-ordered by the topological minor relation. And actually, if you think about it, that means they're ordered by the minor relation as well. So basically, Kraskol had proved the graph minor theorem, but only for trees back in the 60s. So this is what we're going to try to do today, because this one we can actually do in a class. And how do we do it? Well, we'll prove a stronger theorem. So more strongly, they'll be well quasi-ordered in the rooted sense. So what do I mean by rooted? Well, let me define how to, so by rooted you pick roots, of course, roots for each tree. So let T and T prime be rooted trees with roots R and R prime. So I'll establish a stronger relation among rooted trees. So we'll say that T is at most T prime if there exists an isomorphism phi from a subdivision of T to a subtree of T prime that preserves the tree order on VT associated with T and R. So think through that in the writing. What does it mean? So we're mapping subdivisions of T. So we can basically say we can find a subdivision of T in the graph. That would be the topological minor relation, but with an additional property that somehow preserves the roots. So preserves the tree order. What do I mean? So when you take it and you map it, then if X is a parent of Y in T, its mapped images should have the same properties, that phi of X is a parent of phi of Y in T prime. So it preserves, the root will be the closest, of T will be the closest of its kind of subtree to the root in T prime, and so on. So it'll preserve the tree order. So that's what the claim is that we, for our new relation, and then the real theorem is that rooted trees are well quasi-ordered by even this kind of rooted topological minor relation. Okay, so how are we going to prove that? Well, so proof. So we'll finish up with this proof of Kraskol's. So maybe you could pause and think a moment, what trick have we learned so far today? We're doing these infinite stuff. Well, again, it's this minimal bad sequence argument. So suppose not. So again, if there is a bad sequence, then there has to be, you can pick some minimum one. How should you pick minimum? Let's minimize the number of vertices. That makes sense for graphs. So we'll choose T0 to be the start of some sad sequence and minimal number of vertices with respect to that. And then we'll, again, iteratively, we'll choose T1 among all its sequences. That's minimum. And then T2 and so on infinitely, where when we pick Tn, it's going to be the minimum one for after the t0, tn minus 1. So we start with kind of this minimal bad sequence of trees under the rooted topological minor relation. And then we apply kind of a similar trick to what we did before, where we want to use induction somehow. So how should we do this with trees? Well, for every n, we'll let Rn, say, denote the root of the tree Tn, and we'll delete it, and we'll take An to be the set of components. And since we need rooted trees, we'll have the roots of those components be the neighbors of Rn. So when you delete the root, it fractures the tree into new components. We think of those as rooted trees, where the neighbors of Rn are the roots. And we think of those as a set. So we don't think of it as a forest, a rooted forest. We actually just think of it as kind of a set of rooted trees. Why is that useful? Because that should kind of remind you of the set proposition we just proved before. But let's maybe prove a claim intermediately here. So we claim that if you take all the trees that are in all these AN all together, so not as sets anymore, just as individual, but throw them all together, we claim that this is well-quasi-ordered. So why? Suppose not, right? Let T be any sequence of trees in A, kind of will show that this actually has a good pair. And this will establish the theorem. So you take an infinite sequence of trees in A. How do we make any sense of it? Well, for every k, there has to be some nk, let's call it, where tk is in A of n. It has to be in some AN set. And we'll pick k with the smallest nk. So again, using minimality type arguments. So in this infinite sequence, tell me which one first appeared in the A's. Signal that one out. And what I'll do is, by the minimality of nk, look at this sequence. So I'll change my sequence of trees again. We'll do t0 up to tnk minus 1. So keep all the trees, all the decisions we made before we saw one of these trees in our sequence as some kind of subtree. And at that point, then we go ahead and we take tk plus 1, tk plus 2, etc. We add in our trees, and the point is, well, all of those trees, since tk had the minimal among everybody, even everyone else, we could add the other little t's, the t1s as well, superscript ones in. But the point is, everything in the right half of that sequence is in later ANs. So what does that mean? That means that this sequence has to be good, right? Because you're claiming that they're not good, so that they would somehow be bad, right? But then actually then this infinite sequence, if it was bad, would be more minimal than previously. Why? Because t superscript k has to be smaller than t subscript nk, because it's a subtree of it, and so it would contradict the choice of t subscript nk. Okay, that's all good and all, but what do you do with that same argument? Where does this good pair live? So a good pair of the sequence above, if you think through it, well, you can't have a good pair among the subscript t's, because then that would contradict that they were a bad sequence. And for similar reasons, you can't have a good pair between anything in the first half, the t0 up to tnk minus 1, and something in the second half, because again, those are subtrees of later t's, and so then you would also get a good pair. So that would mean there have to be a good pair in that tail, and then that shows that indeed that sequence is good, and so that A is well quasi-ordered. So now we're almost done that we've proved the claim. So we know that the trees themselves are good, right? These trees that show up when you delete the roots as a set are good, but we want to know that kind of the AN is actually good. But that's where our subset lemma comes in, because each AN is a set, a finite set, right? They're finite, because we have finite graphs. And so by our subset lemma, since we know A is well quasi-ordered, A with finite subsets is well quasi-ordered, finite sets. And so then, are we kind of done? Well, yes. So by the sum, since it's well quasi-ordered, the sequence AN has a good pair, AI, AJ, right? So we know somewhere when we delete, RI and RJ, we're going to find a good pair. So here's a picture, right? So we have our TI, we have our TJ, we have our roots, we should be RI and RJ, and then we have AI and we have AJ. And then what do you do? Well, now they're a good pair. What does it mean to be a good pair? It means there's kind of an injective mapping, right? each set in AI goes to some one of the sets from AJ in this rooted minor relation. So it means you can injectively kind of find a subdivision of it where you have roots. And again, they're preserving the tree order. So what can we do at that point? Well, we're basically done, because then Ti, Tj is actually a good pair, which would be a contradiction. How do you do this? Maybe stop and think for a moment. So we kind of embed all of the components of AI. Well, now you map your Ri to your Rj. So we just map the root up there, and then we need to get these paths in. We add the paths from Rj to the images in Tj of the roots. So you kind of squiggle down. You get this new subtree, and if you think about it, then that's a subtree of Tj, which is a subdivision of Ti, and obviously preserves the root order. Now you might think you just need subgraphs, but the issue is actually, if you back up, when you're doing this claim, when we said you didn't find a good pair that's mixed between the two, if you did find an injective pair, right, this would be going from there to some subtree. And so that's kind of why we just don't get rid of subgraph, but we actually need to pick up subdivision, and then we use it here. And so that concludes the proof of Kraskol. So this showed you, at least give you a flavor of this well-quasi-ordering, being this minimal bad sequence argument, and how to prove it for trees. So we'll pick up kind of next time, where we'll look at how can we extend this argument and get more out of it. What kind of graphs are tree-like? In what ways can we show more set classes of graphs that are actually well-quasi-ordered? So of course we won't do the full graph minor theorem, but giving that. But maybe the takeaway from today, we have this beautiful graph minor theorem, applications, for example, knotlessness, just an outstanding theorem, but here's a small beginning taste of the arguments that go into it. So until next time, see you then!